Hi folks, welcome back to 6.1 Verifying Trig Identities, Part 3. So here we're going to take a look at a few more examples, summarize the strategies we've learned, and do one example of a non-identity. Okay, so let's get started with example number 4. So with this one, you'll notice that in this case on the left-hand side, I've got powers of 4, and sometimes I think powers of 4 make us a little bit nervous, but the strategy that we're trying to highlight in this one is actually factoring. Okay, so way back when you first learned how to factor, someone probably said to you, well, a squared minus b squared always factors into a plus b times a minus b. Now, it turns out, though, that there's more to the story. And that second part of the story is that you could say a to the 4th minus b to the 4th equals a squared plus b squared times a squared minus b squared. So we can extend this pattern beyond just a difference of 2 squares. And so we're going to use this second version or extension of this factoring to help us with the left-hand side. All right, let's get started. So instead of a squared plus b squared, on the left-hand side, I'm going to write sine squared theta plus cosine squared theta times sine squared theta minus cosine squared theta. And my goal is to make it look like 2 sine squared theta minus 1. Okay, so some of you might already see that we actually have one of our Pythagorean identities here, sine squared plus cosine squared. And we know from our identity that sine squared plus cosine squared goes to 1. So this left-hand side is really just sine squared theta minus cosine squared theta equals 2 sine squared theta minus 1. Now, I notice on the right-hand side that I have a sine squared, and on the right-hand side I have a sine squared. So what I'm going to do next is try and figure out how can I rewrite cosine squared so that I can have sine squared there instead. And it turns out that, so minus, and I'm going to open up a parentheses here. That parentheses is going to be super important. And cosine squared, another way I can say that is 1 minus sine squared theta. And again, it goes back to that same Pythagorean identity. And now let's distribute this minus 1 and see what we get. Sine squared theta minus 1 plus sine squared theta equals 2 sine squared theta minus 1. Okay, now when we look at this, we might notice that sine squared and sine squared are things we could consider like terms. And so the left-hand side really has 2 sine squared theta minus 1, which equals my right-hand side, which is 2 sine squared theta minus 1. So I've achieved my end goal of verifying the identity because the right-hand side looks like the left-hand side. Okay, let's move on to example number 5. So I've got 1 over secant minus tangent. And when I look at this left-hand side, it is just asking me to use conjugates, like I did earlier in video 2. And so I'm going to go ahead and take this left-hand side, secant x minus tangent x, and I'm going to do times a very fancy way of saying 1, okay? Now, because I'm multiplying by 1, it's not going to change that left-hand side. So secant x minus tangent x, that conjugate is secant x plus tangent x. And if I do the same thing to the numerator, that will make sure that I am multiplying by 1 and not changing the entire equation. And we want that to equal secant x plus tangent x. Okay, let's multiply this out. I've got secant x plus tangent x over secant squared x minus tangent squared x. And we want that to equal secant x plus tangent x. Now when we look at our identities, I hope we see that secant squared minus tangent squared is another way of saying 1. And that leaves us on the left-hand side with secant x plus tangent x, which is exactly what I have on the right-hand side. And so these two sides are equal to each other, which means we have verified our identity. So as you can see, those Pythagorean identities come up a lot, but more importantly, we have to be able to move things from side to side because it's not always just going to be one side of the identity. So we do have to use a little bit of algebra to help us out. Okay, let's finish our identities with one last example before we move on to our counter example. Example 6. So in example 6, I'm also going to take that left-hand side and use it to simplify to get the right-hand side. And I would say this strategy that we're going to highlight here is combining fractions. Meaning that if I had 1/2 and I wanted to add 1/3, I would need to have a common denominator. And so the common denominator for 2 and 3 is 6. So I would multiply the first fraction by 3 over 3. I would multiply the second fraction by 2 over 2. And then I would get 5 over 6. And that's what we're going to do with this right-hand side here. So 1 over 1 minus sine theta plus 1 over 1 plus sine theta. Let's see what we're going to multiply by. The first fraction, I'm going to multiply by a fancy way of saying 1 plus sine theta, and then 1 plus sine theta. So because the thing in the purple, the numerator is equal to the denominator, that's actually saying 1. For the second fraction, the way I'm going to say 1 is I'm going to say 1 minus sine theta over 1 minus sine theta. And I want that to equal 2 secant squared theta. Okay. Let's see what we get. 1 plus sine theta over 1 minus sine squared theta plus 1 minus sine theta over 1 minus sine squared theta equals, we hope, 2 secant squared theta. All right. I can combine those fractions and I will get 2 over 1 minus sine squared theta, which we want to make equal to 2 secant squared theta. And there it is, that Pythagorean identity. 1 minus sine squared theta is the same as cosine squared theta. And I'm going to squeeze this right down here. 2 cosine squared theta is the same as 2 secant squared theta because of the reciprocal identity. And that equals 2 secant squared theta. All right, we verified that identity. So to summarize what we learned so far about verifying identities, let's just make it a point to look over some strategies that we've used. So we have seen that we can split one fraction into multiple fractions. And we've seen that sometimes we actually need to combine multiple fractions into a single fraction. And we've seen that sometimes we need to use conjugates because that actually creates the Pythagorean identities, which helps us when we simplify. We've seen that we can factor expressions. Sometimes we need to use a little bit of our factoring to help us out. And then one last strategy that we've seen is that we can also turn everything into sine or cosine. Now, I think the toughest thing about proofs is it's always some combination of a bunch of different strategies, and you have to be able to go with it, okay? So make sure that you spend some time practicing. Practice definitely makes perfect when it comes to all the proofs. The more you do, the more I think you'll see that we're using a lot of the same patterns over and over again. Okay, so before we finish this video, we're going to take a look at one last example in a category that I call non-identities. And so a non-identity is really when that left-hand side does not equal the right-hand side. Okay, the left-hand side does not equal the right-hand side, and so we run into some issues. It's not actually a true statement. And the easiest way to show this is to actually come up with a counter example, or if you plug in a certain number, if you can show that it's not true, it's not equal, then you've found that it's a non-identity. So here's our example. We've got cotangent x equals the square root of cosecant squared x minus 1. And so I'm going to pick a value for x. I'm going to let x equals 3 pi over 4. And I'm also going to write my cotangent and my cosecant with sines and cosines. So cotangent I can write as cosine x over sine x, which equals the square root of 1 over sine x squared minus 1. And from here, now I'm going to plug in my 3 pi over 4. So cosine of 3 pi over 4 over sine of 3 pi over 4 equals, I hope, 1 minus sine of 3 pi over 4 squared minus 1. Okay, if you haven't used your unit circle in a while, let me just write it up here. I would recommend that you go ahead and bookmark one on your computer or print one out if you have access to a printer, but it will be very, very helpful in this section as well as the next. Okay, so cosine of 3 pi over 4 is root 2 over 2, and sine of 3 pi over 4 is, that is a negative, and sine of 3 pi over 4 is plus root 2 over 2. And let's see if that's equal to 1 over root 2 over 2 squared minus 1. Okay, my left-hand side is going to give me negative 1. So, negative 1 equals 1 over root 2 over 2 is the same as 2 over root 2, just the reciprocal, squared minus 1. So negative 1 equals 4 over 2 minus 1, or negative 1 equals 2 minus 1, or negative 1 equals the square root of 1, and we end up with negative 1 equals 1. And that, folks, is definitely not true. So we have shown here that this is a non-identity, okay? With a counter example where we picked a number that when we plugged it in, the left-hand side did not equal the right-hand side. Okay, so that concludes our videos for 6.1. If you have any questions, shoot me an email, send me a message on Canvas or on WebAssign. I'd be happy to help you out. Thanks so much, folks.